Good morning, good afternoon, and good evening, wherever you may be joining us from. And welcome to this edition of SNIA, Ethernet Storage Fabric presentation. Today we're going to be covering storage performance benchmarks. This is part 5 of a series of presentations we have presented in the past. And during this series we'll be covering workloads. Before I proceed with the introductions, first I want to welcome you and give you a little bit of information on the webcast interface. First thing, you can control the size of the screen. If you'd like to enlarge it, there are a few smaller presentation pieces that may need to be seen in a larger screen. You can do so at the top right-hand corner and just enlarge it to the entire size of your desktop. Next, there's also a chat feature. You can see it, third one down, questions from the audience. We'll be using that for questions. Type your questions in there and we'll be answering them between each section as we change and go forward. There's a large participation of viewers for this webcast, as normal for a lot of the SNIA presentations. So if we're unable to answer all the questions live, we will be posting a blog with all questions and answers after the presentation. As well, we'll also be posting the slides in a PDF and PowerPoint presentation form. Finally, at the end of the presentation, we'd like to ask that each of you rate the webcast and add any comments that may help us to continue to provide the best content and material. Next, this is the legal notice that our lawyers made us put in here. I just want to highlight a couple things before we move forward. The material contained in the presentation is copyrighted by SNIA. If you would like to use it, we just would like to ask you to acknowledge SNIA as the any material that you use. There's a couple other bullets here. I'm not going to read through every one of them, but I will highlight that if you need legal advice on bullet number 4 or a legal opinion, please contact your attorney. A little joke there. Move on to the next slide. A little bit about SNIA. We're the Storage Networking Industry Association. Within this, there are 170 unique member companies. All contribute to making this beneficial for you guys. There's about 3,500 active contributing members out of those 170 groups, companies, and there are about 50,000 end users that follow us and participate in ongoing webinars and activities like this. Next, we'll get on to the speakers today. And I'll be joined by a couple of the industry experts in the storage field. First, we've got Chris Conniff. Chris is from EMC since 1999, EMC/Dell, and where he holds a variety of roles in system engineering, pre-sales, and professional service. In his current role, he's a global business manager for the high-end storage portfolio. And prior to EMC, Chris worked at CSS, IBM, and was a sonar technician in the U.S. Navy. Welcome, Chris. Also joining us is going to be Mark Rogoff. Mark also is with EMC Dell. He's been the SNIA ESF since 2015, specializes in storage and storage performance. Like Chris, Mark's current role is managing the high-end storage portfolio at EMC. And prior to this, Mark was a NAS and SAN storage performance expert in the EMC pre-sales organization. Welcome, Mark. And myself, Tim, I will be, three of us will be your host for today's session. Let's jump in real quick to the presentation. Give you a quick overview, as I mentioned at the beginning. This is storage performance benchmarking, the 5th of the series so far. We started this series back in July of 2015 with metrics and terminology. Moved on in October to solutions under test. March of 2016, the next year, went on to block components. File components was covered that October, and today we're continuing the discussions with workload definitions. If there are individuals who would like to see the other previous four, they can be found on demand within the Bright Talk channel, the SNIA channel. And this one as well, once we are finished, will be posted up there, so you can forward that to other colleagues who may not have been able to make it today or watch it again for reference. Real quick, before I turn it over to Chris, I just wanted to go over the agenda. First will be an introduction. This is going to be covering some terminology. Next, we'll go into the character and what characterizes workloads, how apps interact with different workloads and things that we covered at this point. We'll go into the common workloads, OLTP, virtual machines, and different I/O characteristics that we'll see from these workloads. Finally, we get into some fun, graph with fun and performance. At this point, we'll see read and write patterns of common workloads. And then we'll end with a little summary and go over any final questions that we have. So at this point, I'm going to turn over the presentation to Chris.
Hey, thank you, Tim, and thanks everyone for joining, and thanks to the SNIA org for hosting this forum. I'm excited to be part of it today. So I'm going to kick it over to Mr. Mark Rogoff here.
Thanks, Chris. I'm Mark, so you guys know the name and the voice, and Chris's voice you just heard. And this session, just like all the other ones, is done in the dialogue setting where we go and go back and forth to each other. And with that, it surely should make the material a little less boring. We're trying to make it exciting because we are excited about it. So moving forward, right off the bat, Tim kind of went over on what we have done previously in different sessions. So I'll give you a quick summary of different sessions. Session 1 was in terminology and context. And the main important point in there is that context makes matrix matter. For example, hey Chris, if a storage array gives me 10 millisecond response time, is that good or bad?
Don't know. Depends.
Depends on what?
Well, what we're aiming for and on the context, on the context of it.
Perfect. And then with that, once we understand that all metrics need to have context, we kind of moved on to session number 2, where we introduced the idea of a solution under test. And the solution under test is all the hardware components that participate in running a workload. So on the right, you would have your computers, and all the way on the left, you'll have the drives and everything in between, including protocols and interconnects and switches and everything else, is your solution under test. And the point about that is it's going to have bottlenecks, and the slowest component of that is going to matter most. So it's going to define where your context really lies. Whether you have a problem with the back end, so you're going to be disk bound, you're going to be problem with the front end, so you're going to be client bound. Let's say you have problems with cache at the client.
Or interfaces, you might have inbound interfaces on the front end of the array, right? There's a old joke that we don't fix performance problems, we just push the bottleneck somewhere else. Right?
And that's exactly what that whole session is about. And then the 3 performance principles of how do we push those bottlenecks around. We either do work faster, or we do less of it, or we hire some additional hands to help us. In other words, increase power. And then in session 3, we covered block. Block is the foundation. As Chris likes to say, where does data end up?
On block.
No matter what you do with any kind of data,
Doesn't matter.
it's going to be on block. Even if you go to Amazon today and you say something there, it's still going to live somewhere on block.
That's right.
At the end of the day. So within block, we talked a little bit about what random versus sequential is, and we will cover that today as well in a different angle. We talked a little bit about drives and how flash drives or SSDs are different from sitting drives. And we're actually going to cover a little bit of that today as well. And then we had a whole section on RAID and RAID levels and what goes into that. So I highly recommend somebody who's interested in these subjects to go back and listen to session number 3. But then we moved on and we said block is not everything, it's a foundation, but there's other things existing in the world, and there happen to be file. File appears to be more complex, especially for somebody who is block only trained, and the complexity is bound by the metadata. So we went over and explained how that metadata lives and where it's put together and how it shows up, and how file operations don't align one-for-one to block operations, even though the number of operations in existence is kind of compatible. Both sides have more, except in block we care about which ones, Chris?
Reads and writes.
Just reads and writes. What about everything else?
Yeah, pretty much just reads and writes.
And in file, reads and writes are just normal. They're operations that you're going to see, but you're also going to see a whole bunch of others, which are metadata. So if you're interested in any of that, go back to session 4, please listen to it. You might find out a lot of interesting stuff. Which brings me to today. to say happy Valentine's.
Oh, thank you. Thank you.
We're actually very excited to be here during the Valentine's Day, and because of that, we have hearts on the picture. So I hope you enjoyed our little humor. That's about as funny as it's going to get with the storage guys. So what is a workload, Chris?
What's a workload? Well, it's a discrete application and how that interacts with storage.
So in other words, we send data from the application to storage.
That's right.
And that data is pretty much the way we send it is workload. So if we're going to summarize this whole thing, workload characterizes how applications
Interact with storage.
interact with storage.
Yeah, basically.
That's really in a nutshell. So if you really wanted for this particular message, you've done. Thank you very much. Happy Valentine's Day. If you'd like us to please stay on and enjoy the show.
And that concludes today.
So before we move in, I'm going to turn it over back to Tim. Hopefully we don't have a lot of questions because this was just an introduction, and do a quick check.
Another question, comment.
Yeah, thanks, guys. No questions at this time. The only comments we have are, it sounds a little bit muted there. If you could speak up and speak into the speaker, sit a little closer to it, perhaps.
They will definitely try that. Thank you very much.
Thanks.
So when we dive in to talk about what workload is, the first thing that we'd like to cover is this I/O size or block size. And as we talked about, how application is characterizing how they interact with storage. They send data in this little heart from the picture containing information.
Yes.
And what's important about the size of that heart, Chris?
Well, the bigger the block, the more data it holds. However, the less IOPS or input-output operations a second could do, right? I like to think of them as train cars, right? So if you look at a mile's worth of train tracks and you have train cars which are 1/8 of a mile long, for instance, you could have 8 train cars on that track. Whereas if they were 1/32 of a mile, each train car, then you could have 32 of those train cars on a mile's worth of track.
So because it is Valentine's Day, we have hearts.
We have hearts, yeah.
So the bigger the heart,
The bigger the heart,
there is.
yeah, right, exactly.
And if we go back to the I/O size, what Chris, I think what you just said is the larger the I/O size, the less IOPS there is, and that's the characteristic of the workload. So if we look at the workload and we say, hey, that workload has really large I/Os, what do we expect is going to happen with IOPS for that workload?
The max amount of IOs per second will go down.
Compared to something that has a small size. And that's the point that we're trying to drive with it.
Right.
And after we look at the IOs, the second most important metric that we suggest you look in any workload has to do with reads and writes.
Yes. That's pretty much the two biggies in the block world, right?
And the reason why reads and writes in there, this is why I put the slide from session 3 that talks about the differences between the flash drives and the spinning drives. And what we said in the session 3 was one of the differences between them is that both have a slower performance, but it's slightly off. In the HDD or spinning drives, we have random I/O hitting the drive was kind of slow because of a variety of reasons. In a flash world, it's more of a write because it's slower compared to the read.
Mm-hmm.
Now, overall, the flash drive is not infinitely, but magnitudes, order of magnitudes faster than spinning drives. But within that order of magnitude, just like the bottlenecks. When you change the bottlenecks and you kind of move them away, there's still a slowness on the right compared to the read. Yeah. So what we'd like to emphasize today, Chris, is the fact that the write in itself is still an important metric.
Yes, and there's overhead, right? I mean, you don't get something for nothing. And so if you want an increase in your protection or your data durability to protect against a drive failure, whether that is a spinning disk or a flash drive, this is where RAID comes in, right? So we have to compute the parity, and before we compute the parity, we have to read the parity, then we have to figure it out and write it out, right? So I guess the point of this is that writes have a higher overhead in terms of performance than reads.
Correct. And maybe for summarize, though, if we have more writes on the workload, we have more of that impact that we have to account for.
Yeah.
So going back to the performance, if the workload does a lot of writes, it's going to be kind of slower than the workload with the same I/O size that does a lot of reads.
Generally speaking.
Generally speaking.
Generally speaking, yeah.
Of course, some exceptions. And the next one that we want to cover in the workloads when we define things is the concept of sequentiality and randomness. And what we have here on the screen on the left are two random workloads. And workload 1 and workload 2, on the y-axis, we have physical address. So let's say it's the same disk, for example, but the workloads don't touch each other. They kind of move around. And we compare them to the two workloads on the right, where one workload is the same and the other one is sequential. Because it moves through, as time goes to the right, it moves through the entire physical address space. So Chris, kind of when you look at that, why do we want to look at sequentiality? I mean, is it a good thing? Is it a bad thing? Has anything on it?
So the higher the sequentiality, the easier it is to predict what is going to be next. Right? So if you think about prefetch and read ahead and those types of things, the greater the sequentiality, the better it will be for performance because you can read ahead and those types of things.
So can you show me a little bit how that prediction works, Chris?
Yeah, let's play again. It's easier to show you this way. So I'm going to think of a number. I'm going to say a series of numbers here, right? And I want you to guess which one is next.
When I look at these numbers, I say that the next one is obvious. It's 10.
All right. Yeah, very good. How about this series?
And I think it's sequential, right?
That would be sequential, right? So it'll be very easy to prefetch. If these are logical block addresses, I could go out and grab number 10 and put it into cache, for instance.
Interesting. What do we have here now?
So 2, 4, 8. What do you think would be next in this sequence?
Let's think about this one. I'd say 16 is going to be next.
That's right. Take a look.
Take a look. And it looks like it is indeed is 16. Now, it still says sequential in here, Chris, but aren't there gaps between 2, 4, 8, and 16?
Sure, there are, but it's algorithmic, right? I mean, you get a beat on it. I asked for logical block address 2, then I asked for 4, then I asked for 8. Well, I could see that this is conducive to some sort of pattern, right, by multiplying by 2 to get to the next logical block address.
So now you're saying there's some machine learning within storage arrays that figure these patterns out.
Yes.
Yeah. And some sequential workloads actually are kind of benefiting from the fact that machines are smart.
That's right. We just didn't call it machine learning years ago. It was just an intelligent algorithm. Right? So let's how about take a look at this next sequence here, Mark. 3, 16, 8. What would you think the next number would be here?
Well, I don't know. Maybe a big heart, because today's Valentine's Day.
No, not a heart, but it's some number. So this series was not conducive to any kind of pattern or algorithm, right? So the predictability of a random set of numbers is going to be difficult to guess what is next.
Oh, okay. So when it's random, you have series numbers. There may be a pattern, you don't know what it is. What we're trying to get.
Not yet, no.
All right. So kind of going back to after this game, when we look at the pictures and we compare random versus sequential, we're trying to say that the more sequentiality, the better the predictability and the higher the IOPS are likely on the workload. And this is why we're looking at random and sequential.
That's right. That's right. So the quicker we could get something off of a disk or out of non-volatile memory and furnish it to the host, the better the performance will be, right? Because there is no waiting, the latency is cut down, right? I'm furnishing out of NVRAM rather than having to go fetch it on the back end while the host is waiting.
Very good. All right, well, that means that we kind of put together the 3 big characteristics of the workload. And the first one is the block size, so we covered that, and read-write percentages and random versus sequential. Is that our intent, Chris? Is that how you would be analyzing an unknown workload, by kind of looking at these before you draw any conclusions?
Yes, these are three of the most important factors when characterizing a workload or looking at performance. Yes.
Thank you. All right. Well, again, I'm going to turn it over to Tim. Tim, the mic is open for you. Before we go into the common workloads, are there any questions for Chris and I?
Yes, we got a few questions. I'll try to read this off. The first question is, what about the fact that you get cache effects in the OS stack and also in the flash DRAM landing areas? What actually improves write latencies versus reads?
Yeah, that's a very true statement, and that's why I had said generally speaking, right? So any time that you put some sort of accelerator or caching in front of the disks or even EFDs, that is DRAM or NVRAM, and you have a cache hit or a read ahead, yes, it will greatly improve performance. As far as writes go, that one is a little bit different. So for ACID-based applications that require durability or resiliency, if you have something sitting in front of the persistent storage layer that says, yes, I wrote your data out, and it's lying, it really didn't write it out, if you have a power outage or something go wrong in one of those components, you have the opportunity for data loss or a corruption or something like that. So getting back to those trade-offs, you don't get something for nothing. Under that scenario of writing something in the host and not to the persistent storage layer, you're sacrificing durability for speed, right?
Plus, when you have cache, you're going to add to Chris's explanation, sometimes you may run out of empty slots to accept those writes.
Yeah.
And then what happens is cache has to clean itself up. It has to drain. We call it flushing.
Swap out, right?
You have to swap out. And when that happens, you have these times when you can't send any I/O, and the effect on write is going to be that you have a delay. Now, those happen really quickly in a lot of systems. So, yes, generally speaking, having cache is a good idea, and sometimes your writes are going to come in faster. But on a prolonged period of time, you may not necessarily see the same effect. It depends on implementation, workloads, and all the other things.
Mm-hmm.
I think I have one more question before we move on.
Yeah, next question is it okay to assume sequential I/O would benefit from large I/O size and conversely random I/O from smaller I/O size?
So that's a good question. Not all sequential I/O is large block, and not all random I/O is small block. So we could have large I/Os which are random, and we could have small I/Os which are sequential. So the majority of the time, and we're actually going to get into this, comparing OLAP versus OLTP, you will see that under those two workloads, OLTP does tend to display a small block which is random, whereas OLAP is large block and is.
No, let me get to that.
But, yeah, but they don't have to be, right?
All right, well, I think we're having more questions. And remember, please keep on asking questions and comments. They're all welcome. We're going to answer all of them in the Q&A section that we will post after this is over, probably a couple of days, maybe a week, especially on comments. I see a comment about 248 being sequential or not. We'll have a discussion on that. I think it's a very interesting topic to chat. So we'll move on and we'll talk about how and where and what are different workloads. And so, Chris, we identified a lot of workloads when we were getting ready for this presentation.
Mm-hmm.
And we kind of said, well, when we look at them, when we characterize them all, there are sort of the granddaddies of all the workloads. And then there's other workloads as well. Can you kind of tell me a little bit of the difference between database workload that we see and maybe virtual workload and maybe some others?
Yeah, sure. So depending on your industry vertical, you might have CAD/CAM, computer-aided design, or something that is specific to discrete manufacturing, or maybe you work at a hospital and you have a healthcare ERH system or something like that, right? However, generically speaking, which spans all those, I think as a storage professional, you're more than likely going to come across those top three, which are OLTP and OLAP, as well as quote-unquote virtual workloads, right?
So in other words, what you're going to say is, even though we have more than 3 workloads on the screen here, if we define the database in OLTP and the database warehouse in OLAP, we can set up a stage to be able to define the rest and understand them in a little better.
Sure, yeah, you could apply the characteristics and those 3 big things that we talked about, right? Block size, sequentiality, and
read-write.
Yeah, I'm sorry, thank you. Read-write ratio to any of these workloads, right?
All right, well, let's see if we can actually do that. Here we have a slide on OLTP database workload. And one of the things we want to point out that the design focus of systems that are servicing OLTP are all about response time, or effectively minimizing the response time.
Yes, maximizing the transactions or meeting the maximum amount of transactions at the minimum response time. And it's probably worth, since we're saying transaction, point out, I don't know if it's common knowledge, but OLTP, online transactional processing, right? So going to your bank, going to the grocery store, right? You're doing a transaction. At the end of the day, back at a data center somewhere, that transaction is being posted, a record is being updated, right?
And the intent there is to kind of do that transaction as quick as possible so that you can get your money out of your bank.
Sure, or there might be stock trades, right? And you know, getting down to latency, if me and you are both big brokerage firms and I could shave 2 milliseconds off of my transaction time than you, I'm going to get in at a better price or sell at a better price.
But even outside of financial institution, there's still use cases that could look like a OLTP transaction. That's why we study it.
Right.
So in here, the picture is a little busy, but on the right we have the host sending data to the left in the storage array. And the data is being sent is sort of in 2 groups. There's a bunch of I/O that goes to a table space, and then a bunch of I/O that's qualified as log I/O. What are the difference between the 2, Chris? Like in terms of the I/O size and reads and writes and what we know about it?
Yeah, so basically I look at the table space as the records, right? And they look very much like a spreadsheet in that there's rows and columns, customer name, customer address, dates, etc. Right? So when a transaction takes place, that is where it is recorded in that customer record. However, the log is much like a journal. As a matter of fact, a DBA, you will hear use the term journal more so than log, right? So the logs tend to be sequential because you're starting to write on line 1, then 2, then 3, then 4, and you always write to the next blank line, just like you would in a diary or a journal, right? So
but in general, if you look on the left side, we kind of say that 20% of the flow through the storage array is going to be sequential, and roughly 80% is going to be random, because there's more I/O happening with the table space.
Right, rough and tough.
Rough and tough.
Rough and tough.
So if we summarize this entire OLTP workload in the 3 categories we put forward, we're going to say that the block size is going to be relatively small. And the typical size would be 8 kilobytes, but it doesn't have to be. It could be somewhere around.
Yeah. Right.
And the split between reads and writes is going to be 75% of write. It's a write-heavy, intense workload.
Mm-hmm.
But also the signature here is it's going to be 80% random. The majority of I/O is going to be random, non-sequential. And then put 3 of those together is going to be the OLTP workload.
Yep.
Now the OLAP workload, the next one, it's going to be a little different. And the difference here, Chris, is that we have reads on the table space and writes on the log. Is the database workload always read intensive for OLAP?
Well, no, the data has to be written there first before it can be read. So it's a chicken egg type of thing. But unlike OLTP, so first let me define OLAP, right? Online analytical processing. Right? So OLTP is transactional. This is analytical. So think about business intelligence, decision support, data warehousing, at what price will I maximize revenue and profitability, and all those types of questions that you would look to answer with some sort of OLAP, generically speaking, an OLAP type of application. So during the day, yes, it will tend to be very read intense. Right, so say your firm is open from 9 to 5, and that's when the workers are in, and that's when your stores are open, those types of things. Well, then at 5, once you settle the day, you now might refresh the table space of the OLAP data warehouse or data mart, right, to reflect today's transactions and average balances and what's sold and those types of things. So when it is writing, it's writing, but when it's reading, it's usually doing 100% reads.
So in other words, it's kind of stays sequential no matter what, whether it's reading or writing. So when we look at the left side of the screen, it is more of a sequential workload than it is random.
Typically that's true, yes.
And then the read and write split kind of makes sense there as well. Yeah. So if we put our formula on top of this, we will come up and say, all right, the I/O block size is going to be pretty large. It's going to be roughly about 64 KB, and the read-write split is going to be a lot heavier on the reads than it is on the writes, so sort of the flip opposite of OLTP.
Yes.
And the sequentiality is going to be increased versus randomness.
Yes.
So again, the flip opposite of OLTP.
Right.
And this is why these two, the OLTP and OLAP, sort of the granddaddies of it all, because they're common, they're very pervasive.
Right.
But at the same time, they're kind of flipping.
The inverse, right.
The inverse.
Right. One of them, the design center is latency, minimize latency at the maximum amount of transactions that is needed. Whereas with OLAP, the design center is focused on megabytes a second, right?
So we're going to just push as much data as we can through the pipe that we have.
That's right. So OLTP, it might be an exercise in how many spindles or drives, EFEs, that we give it, right? Whereas OLAP, you might give it more front-end interfaces, right, because of the inverse relation of block size to IOPS that we talked about before, and parallelism. So the only way to get more is to have more front doors and more throughput.
All right. So now let's talk a little bit about virtual. Now, we hear a lot how people come back and say, hey, design us a system that's going to be really good for virtual workload.
Yeah.
And they kind of sit and they wait for the storage gurus to come out and say, yeah, absolutely, I have designed you a system. It's 100% virtual workload ready. It's going to be the best thing you have.
Yeah.
Is that a good way to address the virtual workload crisis?
No, it's about as generic as saying design me a storage solution for an application, right? Or applications. Well, first let me just say, virtualization. When we talk about virtual workloads, there are two big kinds, right? There are where we virtualize servers, we P2V them, meaning they used to be physical, we virtualize them, and they now run on a hypervisor. And then there is the desktop side of the house where I have 1,000 workers in a call center, right? So I'm serving up desktops.
Okay. Well, we're going to talk about desktops later. So on the first side, when we talk about servers,
right.
If we have a hypervisor, and we're intentionally not naming them because they're all, in this respect, are very similar, and they have some virtual machines in there, and then the one is running one OS, the other one is running the other. They're running two different apps.
Yeah.
If those apps were running on physical servers, will the workloads that they would be sending down to storage array be different on physical servers than when they're on virtual servers?
No. I mean, it's so it just so happens that they're now neighbors on a hypervisor, and the hypervisor is doing the I/O as a surrogate on their behalf, right? So getting back to what does the virtualization workload look like? It looks like all of the hosts, or the combination of all the hosts that are on that, being housed on that hypervisor.
Yeah, but then as time goes by, can we always say, hey, this hypervisor A is always going to give me that workload that I see?
Well, you know, a funny thing happens when we take hardware and turn it into software, right, like servers, and they're running here as server A, which is OS, and app A in your picture there. Hypervisors are now clusters, right? So I can have 5 or 6 physical servers, and I can move these workloads around, right? So how it looks today might not be how it looks tomorrow. So even if I got a beat on it and I said, hey, here's how it looked on Monday through Friday, well, maybe next week I move something off, or I got a new client on there or something like that, right?
So what we try to kind of look at it and say, well, we have these component workloads from applications and apps and stuff, and they go all the way to the storage server. You always explained it to me back when I was younger and didn't know anything better, as there's a blender effect.
Yeah, right. The I/O blender, right? You hear that all the time. All the I/Os go in and they get stirred up and sent out to the array. So the workload looks like the combination of all the things that went into the blender. Right?
So guys on the phone and you guys listening to us, if you're going to go out today and you're going to have a little smoothie because of Valentine's Day, for example, drink that smoothie and think of the blender effect, and then that's kind of how we want your mind to anchor, to remember how a virtual workload really looks like. And when we put the virtual workload into a summary, we say, what kind of block size, read, write, and randomness it is, because of the blender effect. It could be anything. It's sort of some weird combination of A's and B's in different points of time.
Right.
And then as time goes along, like Rich explained, in the cluster, when things move around, you get even more of this mixing up in different shapes.
Mm-hmm.
Now moving on, so those were the big granddaddies of it all. Let's briefly talk about some other iconic workloads without going too deep on them. The VDA, the Video Data Acquisition workload, usually looks like, if you imagine 1,000 video cameras recording something and sending down to the storage array, the simplest term. That's the workload where we have sort of an OLAP style, but it's video data. There's a lot of it going one way, and it's all right. It's super large block size, and it's mostly sequential. Mm-hmm. And that's how you might think about it.
Right, right.
What about IoT?
Yeah, IoT is something that is rather newer of a workload compared to the OLAPs and OLTPs of the world, and it's a combination of could be thousands or tens of thousands of sensors that are sending a JSON or XML or text file, right, that need to be written back at the data center, right? So it's a velocity and volume type of thing, and it could be a variety, right, like the big V's of big data and IoT.
And then the VDI that we have in there that we kind of mentioned is a special sub-case of the virtual workload. Yeah. Where we only have the desktops. And the principle there is, unlike when we have some virtual things where everything is super different, the virtualized VMs in there all are similar. They all exhibit sort of being one operating system, the Windows, and they all kind of do the same thing. So there we can quantify it a little bit more. One of the interesting things about that is the block size will vary depending on like the file system formatting or something.
Sure.
And the read-writes tend to be around 50-50, and then I've heard some people say that actually writes a little higher than that. It sort of depends on implementation, and they're super very random.
Yeah, depends on your shop, right?
Depends on your shop.
All of them is going to be a lot different than programmers or CAD or knowledge workers, right?
But overall, one commonality of all of this that I'd like to point out is going back to the same thing. If we analyze workloads on the block size, read-write percentage split, and the random split, we're going to begin to understand what the workload entails in terms of multiple things. Designing a storage system for it or troubleshooting if something doesn't work.
Yes, absolutely.
And on that note, I'll turn it back over to Tim. Tim, I think we have time for one question before we move on.
Okay, we do have a question here in regards to, they want to talk about shifting to I/O size mix. An example given here is SQL Server does many 8K IOs, but log writes at 64K. While many apps are similar to this with bipolar, saying 8 and 128K may be the dominant I/O, averaging to 16 kilobytes won't truly emulate the application. How would you emulate that?
Well, that is a very good point, and I think that we're actually going to answer that in the next section here, and that's the point that we really want to make, right?
All right.
I like to talk about somebody who tells you they have a 150 bowling average. Well, what they didn't tell you is they bowled 2 games in their whole life. One game, every ball was in the gutter, and it was a 0, and the next game, they bowled a perfect 300. You wouldn't gather that from saying, I'm a 150 average bowler, right, to the point. But, yeah, we'll show that.
Do you have time for one more question?
No, I think we need to move on, and we'll answer the other questions.
Perfect.
Because I don't want to run out of time on this. And at the end, if we have time, we'll take more questions. So with that, I'd like to move on to the graph fund section of our presentation, something that I personally enjoy. And the way it works, we play roles, and in this particular game of roles, I'm going to be asking Chris, as a performance expert, to help me figure out what's going on. All right. So here, Chris, on the screen, you have a graph of what I was able to pull from a production system. And I was able to get, and I looked at it in the response time, and I was able to look at some IOPS. But what I really don't know is which workload is this?
That is a workload that is getting somewhere around 1 to 1.5 millisecond response time. Other than that, I can't tell you anything about it.
Are you trying to tell me that you're missing context?
We're missing the context and more information, yeah.
So if you were looking for more information, what kind of information would you be kind of looking for?
Well, some of the things that we talked about earlier, IOPS, block size, random sequential, read versus write, those types of things.
So I could repaint the graph and kind of put IOPS from the x-axis back to the y, and it's going to be a little better. Let's see. All right, well, here I did that. Now we have response time and IOPS going against time. Is that better?
No, not really. I mean, from a graph perspective, it's laid out nicer because the IOPS over on the right side of the y-axis is now in a decrementing order, and I can make more sense of it. The only other thing that I could infer from this, most of the time, they seem to be correlated significantly in that when IOPS goes up, response time goes up, as one would imagine. However, you could see a time slice 7 that really breaks. So, but most of the time, it appears they are significantly correlated.
So what you're trying to tell me is, like, if this was a patient and you were a doctor, you're like, yeah, there's some signs that you're no longer a spring chicken. But you don't know quite what yet. Is it old age or a sickness or something?
I need to order further tests. Yeah. Right.
All right. So which first test do you want to see?
How about we ordered the block size test?
The block size test. All right, well, we'll take a look at the block size and came out, and here's the block size graph that my system was able to give me.
All right.
And it tells me my average block size is 10 kilobytes. Surely you know now what this workload is.
Surely this validates the person who asked the last question, right? That I said we're going to get to it. This is exactly what I was talking about. I see some very high peaks here, and I see the majority of things beneath the average line, right? So I don't have a lot of faith or fidelity in just saying 10K IO average due to those huge peaks that you see there, right? So I would like to see what we call a histogram, right, where I have buckets and I see how many IOs were incremented in each one of those buckets.
And whoop, we have the buckets for you.
There we are.
Now what are we seeing here? That's a histogram.
An IO histogram, if you will. So I could see here that the vast majority is 8K IOs. It happened 25,000 of the IOs were 8K, and only a handful were something others, right?
And so, in other words, you're trying to say that this workload, if we were to qualify it in terms of which block size it has, we'll be using 8K as the most generalization applicable.
That's right.
Even though there's still some other IO sizes happening, which is that normal to kind of see other IO sizes for different applications?
Yeah, sure. Just as the person who asked that question, yeah. Like sometimes to the logs, you will see writes be truncated, right? So instead of me waiting to write 4K, it takes the same amount of effort. I'm going to kind of coalesce all those, right, and then write them all out in 128K, right?
So applying the principle when we said earlier, do less work. You just
do less work.
Get them together and do one.
More efficiently.
As opposed to go back and forth.
You got it.
All right, so which one are we missing in here?
Is it random or sequential? Huh?
I think sequential is not there. How about reads and writes? So here's, after some poking around, I was able to get some reads and writes data. And it looks like that. It kind of tells me, I averaged them out for you so you don't have to guess. And it came out to be that we have about 75% of writes in this particular storage array.
Yeah, so To me, I'm leaning toward a specific workload, but
already.
I am, but I would want to know.
But this is the sort of the data that you would want to be collecting.
Yeah, oh yeah.
Now, do you know whether we always get reads and writes in two graphs, or sometimes do we get one of them and have to deduce the other?
Yeah, that's a good point. Sometimes on most SRMs, so SRM in the original storage resource management, right, which is the software application that a storage professional would use to measure I/O, or an element manager, or whatever you use. Sometimes we'll only represent this as one number, right? And it'll say random I/O. So it will show random I/O as being 25%. Well, you infer that the opposite or inverse of that is sequential, right?
And what about the reads and writes?
Same thing, right? I mean,
so if it's not read, it's a write, kind of fair point.
Yeah, that's right.
All right. So let's take a look at the randomness. And in here we have about 75% random I/O.
Yeah.
And random is in orange, and sequential is in blue in this particular graph.
Mm-hmm.
And what I'm noticing here in this graph, though, is that my random I/O kind of shifts as time goes along. Is that because something's wrong in my system or my workload is super special? Shouldn't it always be just 75%?
No. Sometimes, just like when we played that game, you were able to guess what number was next, and sometimes you weren't, right?
All right. So if I summarize what we kind of looked at, we said, hey, this is predominantly an 8 kilobyte block size. It's a 25-75 read-write split, and it's a 75% random workload. So which workload is this, Chris?
It has all the DNA characteristics of what we just showed earlier, OLTP.
Okay, OLTP. Now, I know for a fact that I'm not running any database in this particular system. So we just looked at it and said it looks like OLTP.
Yeah.
Because I know there's no database,
Right.
Does that mean that your analysis is bogus? Or can we still use it in some useful fashion?
You know, I really don't care if it is OLTP or OLAP. Or being a storage person, really, I am architecting or designing or troubleshooting or benchmarking based off of block size, reads versus writes, randoms versus sequential, right? So it just so happens that we call that OLTP in this demonstration. But those other workloads that we looked at that we didn't really get into and define, they all have those same three characteristics, right? So they're the things that I care about more than anything. It just so happens to be OLTP.
Is it possible that the way I'm looking at it, I'm going to step away from asking questions and do a little bit of a telling my thoughts on the same thing.
There you go.
When you have a performance system or you look at a production system and you looked at a storage workload on that system and you've identified it to some bucket, OLTP, VDI, it doesn't matter which one, as long as you know what that is. Even when it talks about rudimentary stuff, block size, read write, and randomality, you can take that knowledge and use it for your own lab work. When you're sourcing a new solution, you're changing vendors or you have new products and you want to test it out and see how it's going to work in your production. Knowing these three characteristics is going to help you design a test in the lab to see how things are going to be behaving.
Right.
It's also going to help you with troubleshooting. If you know what the workload characteristics are, and then you look at your system and all of a sudden you see that the block size has increased from what you know. That may show that something has changed on the application side that you didn't know about.
That's right.
And when people complain about the response time or the IAP being different and you found out that the block size changed, you may have an answer that actually this is not a sign of trouble, it's a sign of normality. You're sending more data, you may be taking more time for me to process it, or even my IOPS count has to effectively go down because of larger block size.
That's why it's a good idea as a storage practitioner. You use the word change, something changed. Well, change presupposes that you knew it was like yesterday when there wasn't a performance problem, right? So making sure that you have the tools in place and doing the formal, capacity planning, performance management type of discipline over time, such that, when you do get that call, or somebody comes to you with requirements for a new application to put on an array, you know how much is left, and you could see those types of things, right?
Yeah, makes sense.
Yeah.
And with that, I'll turn it back around to Tim. I think we have a couple of minutes before the top of the hour. And let's see if we have any questions for this section.
Yes, we've got a couple of questions here. First question has to do with, do you see reblocking of I/O size when apps are inside a VM versus physical nodes?
What was that?
Can you repeat that question, Tim? Sorry.
Yes. Do you see reblocking of I/O size when apps are inside a virtual machine versus a physical node? And as a follow-on, says, I ask because blocking factors change with versions of hypervisors.
I see what you're saying. That's a very big it depends answer, and to know that for sure, what I would do is I would get a physical SQL host, assuming that it's SQL or something you're talking about, and I would run a task against it and measure its I/O. Then I would P2V it and do the same thing with it under that hypervisor, because they act different at different versions, right? And even based on your configuration, you might have RDMs, in which case it probably is going to behave exactly the same as the one that's physical. So I take it that you're talking about a data store. You know, testing it and looking at it and measuring it each way would be what I would do to answer that question.
Yeah, but as a generic way to say, there's still going to be exceptions. But generically, we still go over the premise that the application virtualized is going to sense the same I/O down the storage array when it's in the physical server.
Sure.
So there could be some other coalescing happening here and there. So yeah, file systems in the middle. You can have a file system inside the VM.
Sure.
You can have a file system inside the hypervisor, which will have some effect.
You might have a cache card in the host. You might have a storage virtualization controller in the middle of it all doing something, right? So it all depends. Yeah.
But generically, I think it's going to, you're going to see the predominant is it's very similar I/O.
It should.
Next question, please.
Okay, next question. Do you see higher write percentages when using clones instead of discrete non-clones?
I'm not sure what that is in.
I think that question was vendor specific, and that's why we're going to admit that.
I don't know. I mean, it depends why you're taking the clone. A lot of people take a clone for read-only to have in their back pocket for operational recovery, in which case there are no writes to it, right?
But there could be different ways of what we call a clone. Like you can copy everything, and you can just do like a snapshot of a clone.
Yeah, I'm not sure what you mean by that. If they want to clarify, we'll answer.
Clarify, and we'll answer that in the Q&A a little more.
Okay.
But just remember, guys, despite the fact that we both work for the same company, this series is meant to be vendor agnostic. So we don't necessarily want to get down to comparing technologies and implementations. Next question, please.
That's one final question here. If you have an all-flash array, what kind of performance hit do you take between sequential and random reads? I would think this isn't as impactful as a mechanical drive.
That's true. It's not as impactful as a mechanical drive. I would agree. Yeah. But when you compare reads to writes, and both of those reads and writes are on an all-flash array, there's a difference.
Yeah, I advise that if you haven't seen session 3 on block technology, go ahead and take a look in there. We actually go into big detail in explaining those bottlenecks and show how the bottleneck on the drive goes really, really small when we put flash drives in there, but then your bottleneck moves somewhere else. But when you fix that other bottleneck, your drive response time goes back up into the visible. So writes are heavy for flash drives for the same reason they're kind of heavy for a spinning drive. Because of the rate
I think they're looking for the difference between sequential and random reads to an all-flash array.
So on an all-flash array, all reads are random, even if sequential at the end of the day by the time it comes into the array. If you think about a spinning disk, it's much like an old 33 or 45 record, right, where it's laid out in concentric circles and those types of things, whereas with a flash drive, it's not the case.
Yeah, again, the same session number 3, we go into technology of flash drives and explain why everything is so random. And once you go in there, you should see why it becomes irrelevant. Every I/O going down to the flash drive becomes random when it's read to write.
But they're so quick, it's pretty much shielded. Whereas if it were a mechanical drive, yeah, a random read versus a sequential read, big difference.
Big difference.
You get 1 millisecond versus 9 milliseconds or whatever.
Sure. All right. So in summary, here's a quick summary of what we have. I think we had done this in the beginning. And what I would like to do, instead of reading this off, please rate this session before you leave, and please leave us some comments. This is the final installment of the series, but if there's interest, we probably can do some more in similar styles, or we take suggestions. But it was my personal pleasure to host all 5 of these, and it was a long journey. And I would like to say thank you to Kim Cantrell, who has been co-presenting this with me for the first 4, and a big thanks to Chris Stinnett for agreeing to co-present this one.
Thanks for having me.
And it was really a big honor to have all of you guys attended. Thank you very, very much.
And I want to give a big thank you out to Mark and Chris as well for the effort put into pulling this presentation together, as well as the presentation itself. Thank you, guys. As a reminder, both a PowerPoint and a PDF version of this webcast will be available on the SNIA orgs forum. You can see the web URL right there. As well, the presentation recording will be available on Bright Talk here in the near future. As a reminder, a full list of questions and answers can be found on our blogs. I'll be following up shortly after this presentation. And also, please be sure to follow us on Twitter. There's a few of the SNIA, as well as our hosts are there, and a few of the other representatives from SNIA as far as the Marketing Association and so forth. Again, thanks everybody for attending this on a Valentine's Day, and again, don't forget to provide any feedback, rate the presentation, and provide us any feedback that will help us to improve further presentations.
Yes, thank you very much, guys. Happy Valentine's Day. Thank you all.